We'll skip the derivation, but the expression on the screen allows us to directly link delta G, the change in free energy, to equilibrium. So I'll give you a quick rundown on the meaning of all the variables in this expression. So the delta G value is the free energy under any set of non-standard conditions. And this is the value that you can use to help you decide if a reaction is going to be spontaneous, non-spontaneous, or at equilibrium under any given set of conditions. The delta G naught, the delta G with that small subscript 0 at the top, is the free energy under standard conditions. And standard conditions are effectively 1 atmosphere, 298 Kelvin, and 1 molar concentrations for any aqueous products or reactants. The R is the gas constant that we've seen before, and specifically, it's the one that is in units of joules per mole Kelvin. Temperature is in Kelvin, and the reaction quotient is the reaction quotient that we've seen many times. So very quickly, we should be able to see if delta G at any random set of conditions is equal to delta G naught if we run everything at standard conditions. We would hope that they'd be the same. So all of our concentrations are 1 molar if we're at standard conditions. And that means that our Q value has to be 1. When you take the ln of 1, you just get 0. So the RT ln of Q term goes to 0. And that means that under these standard conditions, delta G equals delta G naught. So now that we know this expression works, we can recognize that it applies at non-standard conditions. We can look at it under a specific set of conditions. We can look at it specifically at equilibrium. Remember that at equilibrium, your delta G is equal to 0. And also remember that if you're at equilibrium, Q is equal to K. So we can rewrite this expression. So now, if delta G is 0, we know that delta G naught is minus RT ln K. And now we can look at what happens. Under standard conditions. If everything is run at standard conditions and delta G naught is positive, we can see the implications for the value of K. If delta G naught is positive, that implies that at standard conditions, the forward reaction is non-spontaneous. So we can put a positive value into our delta G naught expression. If delta G is positive, that implies that the ln K term must be negative, and therefore K must be less than 1. So if delta G is positive, the forward reaction is non-spontaneous, and K is less than 1, which means that the reactants are going to dominate. And we can do the exact same kind of thing if delta G naught is negative. If delta G naught is negative, the forward reaction is spontaneous, and K is going to be greater than 1, and products are going to dominate. And now we can put this into practice and answer a couple of example questions. If we're given a reaction and then a delta G naught and a temperature, we can find the equilibrium constant for that reaction under those conditions. Before we plug values in, we have to remember that our delta G naught was given in terms of kilojoules, and our R value is going to be given in terms of joules. So we'll have to do some unit conversions to make everything match. So we can find that the equilibrium constant for this reaction under these conditions is 9.96 times 10 to the minus 4. Our delta G was positive, and we found that our K value was less than 1, and reactants dominate, and the forward reaction is non-spontaneous at these conditions. So another question that we can do with free energy and equilibria is we can determine, based on reaction conditions, whether or not a reaction is spontaneous under those conditions. So we need to find delta G and determine if it's positive, negative, or 0. And to do that, we need a delta G naught and we need Q. We're given temperature and we can look up the R value. So our Q value can be calculated using the partial pressures that were given in the question. And we can calculate our delta G naught by looking up tabulated values for delta G's. So you could look up in the back of your textbook or in a formula sheet on a test the delta G naught values for a number of different species. The NaOCl's delta G is 66.3 kilojoules per mole, the nitrogen monoxide's is 86.71, and depending on the table you've been given, you may or may not find a value for chlorine gas. Chlorine gas is chlorine in its standard elemental state, and the delta G naught for any element in its standard state is just 0. So the delta G for this reaction is 46 kilojoules, or if we convert everything to joules, 4,600 joules. Then we can plug all of our values into the expression. Our delta G naught is 4,600 joules. Our R value is 8.314 joules per mole Kelvin. Our temperature is 27 degrees Celsius, but converted into Kelvin, that is 300 Kelvin. And then we have the ln of our Q value, which is just the ln of 1.8. And if we grind all that math out, we find that delta G is 1,512 joules. And delta G is positive, so the reaction is non-spontaneous under these conditions.